In 1877, the summer was so intensely hot that millions of people starved to death in the Madras presidency. China saw up to 3 crore fatalities, and Brazil lost roughly 20 lakh people. Across the globe, crops failed simultaneously during what parts of America called the year without a winter. The root cause of this massive global death toll wasn't a war or a virus. It was a natural temperature anomaly forming thousands of kilometers away, right off the coast of Peru. Normally, Pacific trade winds push warm surface water toward Australia, pulling cooled water up near South America. During an El Niño, these winds weaken. The massive pool of warm water sloshes backward across the eastern Pacific. This immense heat releases incredible thermal energy, completely rewriting the planet's wind and rain patterns. Historically, a severe El Niño was a temporary, isolated event. Before the Industrial Revolution, when this anomaly hit, it would push global temperatures up by about 1.5 degrees Celsius. But human-driven climate change has already raised our permanent, everyday baseline temperature by 1.4 degrees above pre-industrial levels. If the 2026 Mega El Niño stacks an extra 1.5 degrees on top of our already elevated baseline, the net result is a 2.9-degree temperature spike. Human history has no record of a heat anomaly this extreme. For decades, the Earth has been trapping heat faster than it can be released, but we don't feel the vast majority of it. Over 90% of that excess greenhouse heat is absorbed by the oceans, turning the deep Pacific into a massive, silent thermal battery. In early 2026, that battery started to discharge. Trade winds that normally push warm water west began to weaken, acting like an open valve that allowed a massive pulse of deep, stored heat to surge eastward across the equator. To track this surge, scientists had to change how they measure ocean temperatures. This graph compares the traditional fixed baseline model against the new Relative Oceanic Nino Index, or RONI. Because the oceans have grown so warm globally, researchers use this moving RONI baseline to isolate the specific El Niño heat pulse from the overall global warming signal. When we look at the RONI data for April 2026, the severity of the pulse is clear. In the easternmost equatorial waters, known as the Nino 1+2 region, temperatures rapidly spiked 1.8 degrees Celsius above the surrounding ocean mean. The sudden release of that much stored oceanic heat into the atmosphere makes this event mathematically highly likely to push the planet's average annual temperature past the 1.5 degrees Celsius warming threshold. The physical wave of warm water crashes first against the South American coast. Here, the immediate ecological response is a rapid breakdown of the local marine habitat. Off the coast of Peru, surface waters reached 29 degrees Celsius early in the year. Anchovies, which prefer cold water and drive a massive fish meal industry, are forced to dive deeper or migrate south to escape the heat. In response, the Peruvian government launched an early, desperate fishing season with severely reduced quotas, scrambling to catch the biomass before it disappears entirely. Further out in the Pacific, that sustained thermal stress breaks the partnership between corals and the microscopic algae that supply their food. The coral expels the algae and turns bone white, leaving the structure starving and brittle. Reefs typically require a decade or more to regenerate from a severe bleaching event. With ocean temperatures climbing, these mass bleaching events are projected to occur almost annually, permanently closing the biological window these structures need to rebuild. The marine environments absorbing this initial impact face an immediate loss of structural complexity and biodiversity. As those foundation species collapse, the coastal economies built on top of them follow suit. As the heat transfers from the ocean to the atmosphere, it aggressively alters weather patterns inland. Along the typically arid Pacific coast, the warming triggers a sudden tropicalization of the local climate. In March of 2026, certain coastal weather stations in northern Peru logged 160 millimeters of rain in just 3 hours. The bone-dry, compacted soil couldn't absorb the deluge, leading to massive surface runoff and landslides that swept through cities. Move inland over the Andes to the Amazon basin, and the atmospheric effect reverses. The El Niño pattern suppresses rainfall, leaving humid vegetation completely desiccated. When fires ignite, they spread deep through the dry root systems and organic matter, burning underground for weeks. Where the forest meets agricultural land, this drought triggers what ecologists call the edge effect. Specialist trees with dense wood die off and are replaced by fast-growing, drought-tolerant grasses and generalist species. The diverse canopy homogenizes, making the perimeter highly combustible. This aridity breaks the natural flood cycles that species like the native acai palm rely on. Traditional harvesters, facing a 35% drop in crop yields, are being pushed to abandon wild extraction. To keep producing the berries, they have to clear competing trees and install artificial irrigation, draining more water from an already parched landscape. On the other side of the Pacific, the atmospheric pressure shifts are converging over Australia. Here, the warm El Niño aligns with a positive Indian Ocean dipole, a pattern characterized by unusually cool waters to the continent's northwest, which cuts off typical moisture flows. Meteorological data from May to July points to extreme rainfall deficits across eastern Australia, paired with over a 70% probability of unusually high maximum temperatures. The dry winter sets up vast expanses of the country for a highly volatile bushfire season. Across these continents, the weather extremes force communities into a corner. When farmers heavily irrigate dry forests or fleets rush to catch migrating fish, those necessary survival tactics end up straining the very ecosystems they depend on. The physical stress on land inevitably fractures the complex network of global food production. The atmospheric shifts heavily suppress the South Asian summer monsoon. Without that seasonal rainfall, crop yields for global staples like rice in India and maize in Southeast Asia experience significant drops due to severe heat stress. This chart correlates the historical dates of major El Niño events with global cereal yields and commodity prices. When harvests drop, major producing nations implement export restrictions to protect their own domestic food supply. This creates a feedback loop. International markets panic, soft commodity prices surge, and farmers, already burdened by high fertilizer costs, reduce their planting, driving yields down even further. A few degrees of warming in a specific zone of the equatorial Pacific mathematically translates to lower grain harvests and higher grocery bills across the globe. Beyond the failing crops and bleached reefs, this thermal shockwave takes a direct physical toll on the human body. Researchers analyzing 6 decades of mortality records have identified that these major warming events persistently slow down the long-term improvements in life expectancy across affected nations. The spike in mortality is driven by a combination of compounding environmental hazards. Floods cause sudden surges in waterborne diarrheal diseases, while extreme heat taxes the cardiovascular systems of the elderly, and thick wildfire smoke sharply increases respiratory failure in dense urban populations. This chart compares historical economic and life expectancy losses against future projections. While the 1982 and 1998 events reduced life expectancy gains by about half a year each, the future is much steeper. Under current emission pathways, researchers project that by 2100, the intensifying El Niño cycle will result in a cumulative loss of 2.8 years in life expectancy, mapping directly to $35 trillion in global economic damages. Dealing with these events through emergency relief and post-disaster cleanups is an unsustainable math problem. Preserving health requires overhauling water infrastructure, building heat-resilient agriculture, and deploying comprehensive early warning systems before the heat pulse ever arrives. The 2026 Super El Niño proves that we are no longer waiting for the climate to shift. The thermal battery has been discharging, and protecting coastal societies and inland economies